Hey everyone! Today we're looking at PROFINET, which is one of a number of examples of industrial Ethernet. So, what's the difference between standard Ethernet and industrial Ethernet? Well, a lot of the time, not much. And generally speaking, industrial Ethernet is a standard implementation of Ethernet plus some bells and whistles that provide some level of determinism to allow real-time control of industrial processes and machinery. This means it's possible in most cases to use standard Ethernet cabling and switches, but as these installations will tend to be in harsh environments that can have any combination of temperature extremes, vibration, electrical noise and fluid sprays, there are also a wide range of ruggedized and watertight Cat5 and Cat6 cable options with metallized RJ45 connectors or even M12 or M8 connectors. Some of the heavy hitters in this arena include protocols like EtherCAT, Ethernet IP, Circos3 and of course PROFINET. The main differentiator between these variants is how they go about adding the bells and whistles. To understand how these add-ons work, we need to revisit the OSI model. Now, if you remember the OSI reference model, it gives us a way of conceptualizing a network connection using 7 abstraction layers that are helpful for us mere mortals to get our heads around what's going on. In industrial Ethernet applications, there are usually some form of modification at the MAC layer in order to get low latency and deterministic response times. It's what these mods are and how they are used that differentiates the various solutions on offer. For example, EtherCAT and Circos operate at the MAC layer and are transparent to higher level Ethernet protocols like TCP/IP or web servers. They operate by having slave nodes process the datagram and insert their data onto the frame as it passes through. This is all in hardware, so it has minimal latency. By contrast, Ethernet IP and PROFINET are application layer protocols that essentially reside at the top layer of our OSI model, but they have MAC layer mods that give the application real-time attributes. We'll go into exactly what these are for PROFINET in a moment, but first, a little history. Come with me, if you will, back to the end of the 1980s. This was when field bus options first started to become available to industrial automation manufacturers. A field bus is a standardized network that connects controllers like PLCs with their peripheral devices like sensors, actuators, and even control panels. The way the network is set up allows real-time distributed control over industrial processes and machinery. Each field bus standard generally supports a number of network topologies, from simple point-to-point through more complex arrangements like spurs, rings, daisy chains, and trees. This allows users to choose the most effective setup for their manufacturing environment. The most prolific field bus in terms of installed equipment is Profibus, which is an amalgam of process, field, bus. This came out of a broad research effort backed by the German Federal Ministry of Education and Research that began in 1986 and included teams from 21 large manufacturers and research institutes in West Germany. Unfortunately, the resulting specification turned out to be overly complex for real-world use. But in 1994, Siemens revisited the idea, simplifying the spec into something usable that became known as Profibus DP, or Profibus Decentralized Peripherals. This turned out to be a hit in industrial control circles with over 60 million nodes deployed as of 2018. Okay, that's a pretty impressive success, but what's that got to do with PROFINET? Well, if you think of each chemical or manufacturing process being controlled by a field bus as an autonomous subsystem, then the next logical progression is to take these subsystems and connect them together, so that the entire chain of manufacturing processes for the entire facility can be centrally or even remotely controlled. One of the useful features of using Ethernet in this capacity is its near universal use in corporate IT infrastructure, which means it's well understood and low cost. Using industrial Ethernet proxies to connect Fieldbus and other subsystems together with otherwise standard IT infrastructure means that you can gather systems using different Fieldbus protocols such as Modbus, DeviceNet, Foundation Fieldbus and of course PROFINET under the control of a single system. That can also control any other autonomous systems like production line robots. This allows automated start-to-finish control of the entire manufacturing process at a facility from a single point. That point could even be remote, using existing corporate IT infrastructure and security restrictions. So that's why you might want to use an industrial control network. The next question for us is, how does PROFINET work in that context? So we'll begin by defining some terms. First off, when we're talking about an I/O controller, we usually mean a PLC, although of course it doesn't have to be. But it's a programmable device that's set up to run one or more automated processes. An I/O device is pretty much every other sensor or actuator that's connected to the controller, to either monitor or physically carry out an automated process. I/O controllers and I/O devices in network terms are exchanging what's known as cyclic data. This is the time-sensitive data that must go back and forth to keep the application running. The one other type of device that you may find on a PROFINET network is an I/O supervisor. This is usually employed in commissioning or diagnostics and will quite often be removed after use. This configuration and diagnostic data is known as acyclic data and isn't time-sensitive. So this can be sent outside the bandwidth required for the cyclic data. Each device will, of course, be uniquely identified, first by its MAC address, which will usually be fixed as a factory default, its IP address, usually assigned by DHCP, and a device name that will be allocated on commissioning. In terms of the naming convention for the network interfaces, they are labelled X plus a digit, so X1, X2 for each interface. Each port will be P1, P2 and so on, and if it's a ring port it will be labelled as such with an R. So for example X2P1 means interface 2, port 1. And in our image the green Ethernet cable is plugged into interface 1, port 1. Okay, so now we know that. The next thing we need to understand is how the functionality of PROFINET is set up to ensure interoperability of devices on a network. This is done through a set of 3 conformance classes, which clearly define the minimum functionality required for each class. The conformance classes each build on top of the functionality of industrial Ethernet, and each class builds extra functionality on top of the one below. And these are essentially set up to meet increasingly stringent application requirements. Conformance classes A and B both support real-time data transfer, while Class C supports tighter constraints in the form of isochronous real-time transfers. And we'll explore what that means in a second. But let's start by defining what we mean by real-time. To be considered real-time, a system must be deterministic. This means that tasks must run to completion within a defined time period with a 100% success rate. So, if you run a set of tasks many times, the outcome and the outcome order should always be the same. This consistent and predictable execution is determinism. So as we can see in our diagram, from the moment the resource becomes available at release to the completion of the task, the response time must fall before the deadline, including any setup required to fulfill the task. In a network situation, this means the system must guarantee both enough bandwidth for the data and a maximum latency for the transfer. Of course, in any real-world system, there are going to be variations in the actual timing of this latency, and this is referred to as jitter, and this jitter should be measurable and minimized to guarantee the system performance. In terms of application areas, there are 2 categories of real-time operation. Soft real-time, where there's a specified cycle time for task completion and there's an expectation that this will happen, but a violation of the deadline can be tolerated by the system. For example, real-time animation in a computer game, where missing a deadline might mean a skipped frame, but it won't cause a system failure. Then there's hard real-time, where a breached deadline is a catastrophic failure. For this category, you can think of motion control systems or engine management systems, where a missed beat could cause a literal material failure of the system and lead to injury or death for any people close by. For PROFINET, RT covers soft real-time applications, while asynchronous real-time is aimed at hard real-time applications. Now, if you've got a little voice in the back of your head saying, well, I didn't think Ethernet was deterministic, then you can buy your little voice a beer. It's right. Ethernet uses switches to create point-to-point data transfers. This eliminates the collision and resend problems that you used to get when multiple nodes would share a collision domain, as a switch essentially creates multiple private links between itself and each node it connects to. This is what's known as a bridged network, with each switch in the network acting as a bridge between endpoints. This type of network is pretty much self-configured, but to do this, each switch uses a store and forward strategy, where the switch will receive the entire frame into memory before forwarding it on. This allows the switch to make some important processing decisions based on information in the header. But there are some negative effects to latency and reliability when using this store and forward mechanism. There will, of course, be a delay caused by reading in the entire frame before passing it on, and this delay will be a function of how long the frame is, which could be as long as 1522 bytes, and that equates to about 124 microseconds for the 100 megabit Ethernet that PROFINET uses. And if the output port is already sending a frame, our current frame will have to wait till that frame has been sent before it's forwarded. These delays will multiply across cascaded switches, creating fluctuating latencies, or jitter. Also, as switches don't have infinite storage, they will discard incoming datagrams if the buffer is already full due to heavy network traffic. And that is obviously a major reliability issue. Luckily, there are a few things at the MAC layer that we can do to boost both determinism and reliability without needing any specialised hardware. One thing that PROFINET RT datagrams do is to make use of the ether type field, setting it to a value of 8892 in hex. When a PROFINET station receives datagrams with this ether type, the data is immediately transferred from the MAC layer to the application layer, skipping the processing required for the intermediate layers and improving both speed and determinism of the operation. PROFINET also takes advantage of MAC layer quality of service features in the optional VLAN tag that can be inserted into the frame in front of the EtherType tag. This VLAN tag has a 3-bit priority marker as part of the IEEE 802.1p class of service standard that can be used to get switches to move high priority data before lower priority datagrams, reducing the latency for our cyclic data and effectively giving it virtual bandwidth segregation. Also, the next bit along from this priority marker, the DEI bit, can be used to mark datagrams as being okay to drop at times of high network traffic, and this is another way of giving important data more reliability in transfer. So what this means is that Conformance Class B of PROFINET RT can accommodate the kinds of transfers required by factory automation applications, where the response times are anywhere from 10 milliseconds down to around 1 millisecond. For motion control drives and servos that require much tighter constraints, we have to turn to Conformance Class C, which is Isochronous Real-Time PROFINET, or IRT. This can achieve cycle times as short as 32 microseconds, with less than 1 microsecond of jitter. But to do this, we need some hardware enhancements. IRT uses a form of time division multiplexing to cordon off bandwidth exclusively for IRT data. The 100 megabits per second transmission bandwidth of Ethernet is divided up into fixed equal cycle times. Within each cycle, the time is further divided into phases. The red phase is reserved exclusively for Class C real-time data. After that, in the orange phase, Class B messages get a go, And then the cycle is open to any non-time critical data, whether that's PROFINET data like diagnostics or standard Ethernet traffic. To create these fixed-sized cycles, all of the devices involved in the IRT application need to be precisely synchronized. This is done using an extended version of the clock sync in the IEEE 1588 Precision Time Protocol that includes automatic determination and compensation of the network transmission time, giving us that lower than 1 microsecond jitter. But if we're going to ensure that even maximal sized Ethernet datagrams can pass through transparently during the green phase, then the green phase will need to be at least 125 microseconds long, meaning that we wouldn't be able to get a cycle time under 250 microseconds. This problem is tackled using a fragmentation mechanism, where green phase datagrams can optionally be broken into fragments. These much shorter segments are sent across multiple shorter time frame cycles and reassembled at the target devices. This means we can reduce cycle times for our real-time data to meet tighter time constraints, with cycle times as short as 31.25 microseconds, while still carrying standard Ethernet frames. This fragmentation is transparent to other Ethernet nodes, so they are unaware that this is happening. Some other methods used by PROFINET to increase network efficiency include fast forwarding and dynamic frame packing. So let's start with fast forwarding. For the integrated switch of a network node to decide whether or not it needs to forward a frame on, it needs to be able to read the frame ID. In a standard frame, this is quite a way back in the frame, so it can take around 1440 nanoseconds to read in. Fast forwarding puts the ID at the start of the frame so it can be read in as little as 320 nanoseconds, which means the forwarding delay can be reduced from 3 to 6 microseconds down to 1.2 microseconds. In dynamic frame packing, each frame from the controller includes datagrams for each node in the daisy chain. When the first node receives the frame, it removes its datagram and only forwards the other datagrams, shortening the frame length going forward to the next node. This next node will do exactly the same thing, reducing the transit time with each node. As Ethernet is full duplex, frames going the other way towards the controller will add datagrams as they pass through each node, providing an efficient use of the available network bandwidth. To finish up, let's briefly run down the support mechanisms required to be compliant with each conformance class of PROFINET. Starting with Class A, it will, of course, support cyclic data exchange with soft real-time properties. This means cycle times from 1 to 512 milliseconds. It also supports acyclic data, like setup parameters and diagnostics. And there's an alarm model for device and network errors that rates them as good or defective. Plus, there's an optional maintenance request and urgent maintenance demand warning that can be implemented. All conformance classes define IEC 61784 cabling, but Class A also allows wireless comms. Switches need to support the VLAN tag for prioritization. Class B expands on the Class A requirements and includes additional network diagnostics, plus network topology detection using LLDP and SNMP. The Link Layer Discovery Protocol, or LLDP, is a Layer 2 protocol where device information like the chassis ID, port ID and description, and the device capabilities are stored in a local management information database known as an MIB, which can be queried using the Simple Network Management Protocol, or SNMP, to build up a picture of the network topology, and this of course will improve network diagnostics. In Class C, the minimum update rate is defined as 250 microseconds, though as we've discussed this can be reduced to as low as 31.25 microseconds, with a maximum jitter of under 1 microsecond. The cyclic data is transferred as synchronized packets on reserved bandwidth, while all other data shares the rest of the Ethernet bandwidth. For completeness, we should mention that there is also a conformance Class D, which essentially offers the same services as Class C, but uses the IEEE's Time-Sensitive Networking, or TSN, set of standards. Many of the TSN standards are still in draft form, and it may be a little while before you encounter any deployed Class D systems. So, that is our brief look at the world of PROFINET, and all that remains is to say stay safe and see you soon.